Actually, I'm not going to teach here. This talk is more about like my reflection on what's going on with important functional programming languages. So that's my idea behind this talk. So I look at this area of functional effects or effect systems, and I try to understand what do developers want, like currently, because programming languages are supposed to solve issues that developers have, right? And then I also observe programming languages, and I try to understand what those programming languages can provide for us to solve our issues. Or maybe their goal is somewhat different. Maybe programming languages don't serve software developers. Maybe they do something else. So this talk is mainly about that. So my reflection on these topics. But in the area of functional effects. And so I called it like functional effects in perspective. So I would like to show you this, how it started and how it goes. So let me first show this quote. It is not very famous, to be honest. And you don't have to read it, because I will read it for you. But you will see how important it is. So it's a quote from one research paper. I will tell you which one later. So, and it says, this schema critically relies on the distinction between a complete program and a nested program phrase. Like you have a program, and then you have some part of that program, okay? A complete program is thought of as an agent that interacts with the outside world, for example, a file system, and that affects global resources, for example, the store, right? So maybe it's printing something to the, like it's using printer or display or something like that. A central authority administers these resources. So there is something that administers resources outside of our program. The meaning of a program phrase is a computation, which may be a value or an effect. This is like actually one of the first uses of this word effect in this context. So if the meaning of a program phrase is an effect, it is propagated to the central authority. So if we have some effect, like a request to do some input or output, then we refer to that central authority outside of a program to do something for us. The propagation process adds a function to the effect package such that the central authority can resume the suspended calculation. Look, this is important. So we say here, we have the central authority. We delegate something to it. Please do that for us. And then please continue our computation at some point. Right? So we are going back to our program, and we are going to do something else. We refer to this component of an effect package as the handle, since it provides access to the place of origin for the package. So we are handling something, and then we get back into our program and continue our computations. So this quote comes from the 1994 paper, 1994, so we can celebrate 30 years to this paper. It was written by Cartwright and Felisen, and it is called, like these fancy, we functional programmers, we like those fancy names, but PL, programming language theories, they like it more. Like this paper is called Extensible Denotational Language Specifications. So it is very difficult topic. If you read it, then, well, it's very difficult to understand anything. It's like mathematical paper. But this effect thing originated right there. And you might know that monads, were originated also in some kind of similar settings. When Eugenio Moggi tried to solve some problems with denotational semantics, and then he discovered this idea of a monad. So the same thing happened with effect programming, but the result was a little bit different. Between this discovering an idea of a monad and implementing monads in a real programming language, Haskell, it took like 7 or 8 years. But this paper was hidden for many years, actually. And nobody in the software development and programming language world actually thought about anything like that. So 1994. And then we got to this moment, and now, as Juan said, it's a very hot topic, and we are discussing it all the time, and every conference needs some talk about effects. But the idea comes from 1994. Several other steps. So what we can actually do, it follows from that paper, to be honest. So we can read or write mutable state with effects, because those are effects, effectful computations. We can implement I/O operation with that. So we can interact with the user. We can also throw an exception, because what is throwing an exception? We say, well, at this point, so our effect is going to be this. We just remove huge part of our program, that program phrase, and we go back to some exception handler. So it's the same idea. So effect is going back somewhere where we catch that exception. And it is also possible to implement other non-local control flow operators. So these things that we have in different programming languages, like Python generators, when you generate a list by saying which elements go to that list, or async programming, or lightweight concurrency. So all that stuff, non-determinism, all that stuff can be modeled with effects. And it was pretty clear for many years. But monads were much more popular. Monads got into real programming language, and monads were kind of covering the whole story behind effects. So we didn't need anything else. But of course, we always knew that there are some problems with monads, and especially if you want to use many different effects in one program, then you need to learn something about monad transformers and a lot of difficult stuff. So, but still, effects were kind of hidden. And then in 2013, there was this another seminal paper by Oleg Kiselov about extensible effects, and he actually quoted the same quote from Felizen paper. So Kiselov read it and actually knew about it. And his idea was to implement something like that in Haskell. So if you read that paper these days, it's kind of difficult because, Oleg Kiselov is known for complexity. He uses type systems. Maybe some people say that he abuses type systems, and it's very easy in Haskell to abuse that. But still, it was something, not very convenient, but it was just a start. And since that time, we've got the whole area of so-called types and effects systems. So type systems which are also able to track effects, if you are doing non-determinism in this function, or you are doing I/O or something else. And then there were many research languages for effects. These are just a small list of those languages. And the idea behind those languages was, what if we make effects first class? not something that is implemented via something else, but we make it first class, and how we can use that, what we can do with them. One of the most important points at this development of those language was the idea that we can easily separate so-called effects and effect handlers. So there is a part where we describe our effects, but we don't actually implement them. So we do something declaratively. We say, well, at this point we will do this. At that point we will do that. But we don't actually do. We just describe what we are going to do in our code. And then there is another part, which is effect handler, which is responsible for actually executing that stuff. So this separation, it was not there in the very beginning, but it at some point researchers realized that it's a good idea to have this sort of modularization and distinction, separating between these two things. In some programming languages, and mainly in Scala, this whole idea of effects becomes like really first-class important idea. But it was implemented via monads, and because of that problem with structuring monads and monad transformers, in Scala they mostly end up with one single, like some people say, God monad responsible for everything. And you can do something like functional effects there, but you just lose a lot of stuff that was promised originally, where you can control, like in a very like atomic way, those effects. So you don't want to combine everything into one big monad. You just want to act separately. But still, this is like very important industrial practice, and a lot of projects in nowadays Scala just uses that approach, and it's very powerful. And what is more important, it is practical, so it works. And another approach, which is relatively new one, is when we have some so-called direct embedding into a programming language. When programming language decides to implement effects into their core. So, and we don't need this mediator, this monad. We just have effects and we use them. So this is a brief history. So we started in 1994 with that idea, and then 20 years of silence. And if you try to look at like academic papers about effects, there are hundreds of them, and like literally hundreds. It's not like I'm making this number up. There are a lot of them, and it is a good example of a lot of research that eventually ends up in something practical, in implementation in a programming language. Okay? So let me show this example in F programming language. It's one of those research languages. I will show you several examples in several programming languages, and chances are you don't know them, and that's fine. And in fact, you don't need to understand everything. Like you know, when my students ask me, like, I don't understand monads, what should I do? My answer is, you don't have to understand monads. Okay, you can use them without understanding, so you don't need to understand. You just need to get several simple ideas. Like for example, here effects in F are first class, so we declare them like this. So very simple syntax. We just say this is effect, and this is like declarative stuff. So we say it is this effect. Just only have it just have type, and that's it, nothing else. Then we also have a handler. So this is an implementation of a handler here. Yeah, F uses sort of ML syntax, familiar to some folks here, and there are several important parts. When we say effect handler, we need to say, what should we do when we get effect? What should we do when we get set effect? What should we do when we complete this handling of effects? So final stage, what should we do at the end? What should we return at the end? And then one of the most important parts. What do we do if we have something else here? And the thing is that this something else might be some other effect. Some effect we don't know anything about it. So we just have this, it's like wild card. We skip it. And this is the basis for composing effects. So you can use like these effects and then other effects. And in this handler, you just skip them and you don't think about them. So you have implementation for your effects. You say what to do when it's over. And you also say how to skip other effects here. And it doesn't matter, they have some implementation. It's like state monad, if you are familiar with that in Scala or in Haskell. So it doesn't matter. The thing is that we have this handler. What matters actually is that in this last part of this code, we have actual code using effects. Like we say, we perform something. So we perform get. So we ask that central authority or handler in this case to perform this effect, then that effect, and then return something as a result. And you can see here that inside this with handle block, it's imperative code. So this is what they usually call direct style. You don't need monads inside that. And you just do effectful programming. And you can reason about them. You can get all those functional programming nice things right here. So, but this was a research language. So nobody implement like servers, backend applications in F. That's not its goal. But its goal was to clearly show that it is possible to do something interesting with this separation. So in that original paper, you had this idea of central authority. And now we don't have central authority. We have many authorities responsible for many kinds of effects in our program. And here I have only one kind of effects, but you can easily add other effects, and you can also add other handlers. So you have handler, and inside that another handler, and another handler, and then finally you get your code in imperative direct style. So that's an idea. How we can actually implement that? There are many approaches, and one of the most practical, provably practical approaches is so-called delimited continuations. Like this conference, I listen to several talks, and I always see these words like continuations are everywhere, like effects are like were mentioned in several talks. So I will tell you several words about continuations as well. So this example is in Racket, and Racket is developed by not that guy Felizan, but under his supervision. So he's a guy behind Scheme programming language and Racket and delimited continuations and that idea of effectful programming, right? So very big guy in programming languages world. And in that language, they have some built-in tool, which is we can say delimited continuations API. So you can do things like that. So here in this example, we are going over a list of numbers, and we try to compute the sum of those numbers until we met some special element which doesn't met some condition, or which actually met some condition. So we sum numbers until we met some specific element. So you can imagine you have an array of numbers and you go over it, and if some element is wrong, you just exit that computation. You don't go over other elements, over the rest of the elements. And this is how they can implement it in Racket. So what is important here? So this line just says so that we want to use those control operators. And this is the first control operator, which is called reset. And you can see that reset gives you part of your program. If you remember program phrase, so it's exactly program phrase, so part of your program. And you delimit, hence delimited continuation. You delimit, so set limits to this fragment of a program. And then inside that program, you have another operator, which is called shift. And the idea behind shift is as follows. So this first argument, k, which is exactly continuation, and in this particular case, we return sum if we are here. And in general, in this implementation of this returning element, you can write anything, including calling k. And what is k? K will be actually the same fragment of this code. Everything inside reset. So look, you have part of your program, and you can call it, for example, several times if you want. And it's a little bit difficult to understand. You need to look at those examples like for many hours in order to realize what's going on. But in general, idea is simple. So you operate with part of your program, and you can call this part of the program several times, or you can at some point say, well, I don't want to call it. You just return a result, and that's it. And it turned out that using this technique, it is possible to do all sorts of things we have in modern days programming languages, like exceptions, concurrency, and all those effects that I mentioned in the beginning of this talk. So one single tool inside a programming language that can implement a lot of stuff that we actually need. And in some programming languages, it is important to have these low-level constructs to do stuff. In some other programming languages, they prefer to hide low-level stuff and provide you much more high-level tools for doing things. So these are different approaches to implementing programming languages. So in Racket, they give you this API, 2 functions, and then you can implement almost everything in which looks like effectual programming. All right. Now, I promise you to talk about these 2 things. Like we have software developers and they want something, and we have programming languages and they provide something. So let's talk a little bit about this dichotomy. So this difference between these 2 actors in the area of software development. By the way, I myself, I don't write production code. So that's not my job. So I'm not struggling with like bad parts of programming languages. I'm lucky. What I do, like for many years I was teaching students. For many years I was observing programming languages. I was observing software developers. So I know who they are. And I know what they want. And I know what they don't want. And I also know that programming languages don't serve. Maybe that's a breaking news. But programming languages don't serve developers. They serve their designers, in fact. So in many cases, so programming languages are like something which developed by themselves. Because sometimes in this programming language, it's just impossible to do that stuff. You just need to do it differently. So those are like living creatures sometimes. So you cannot do something which is not like in the spirit of this language. Okay? So, if you want to introduce some big thing into a programming language, then we can analyze like why we do that. So what software developers want actually. And they can think about, well, they have their practical problems. For example, some developers do want to control effects. Okay, so they want to know, like they want to reason about their programs. They want to know, here I have mutable state, here I don't have any mutable state. They need some assurance. They also want to have some sort of expressivity. So they need that programming language actually express what they want, allows them to express what they want. And they don't want to write thousands lines of code to do something simple. So they need that expressivity. Sometimes they need those nice things that we usually have in functional programming, like composability, stuff like that. Some folks prefer simplicity, right? That's not about Scala folks, of course. They don't like simplicity. But in other programming languages, that's an important point. Some of us want efficiency, so we want our code to be performant because, well, we serve millions of customers every second. Those are things which developers think about. But if we look at the other side, so we have programming languages and we have programming language designers, and they think about some other things. So, for example, they want to make their changes minimal because it's not a good idea to rewrite the whole programming language from scratch unless you really want that. Okay, so in many cases you just want to introduce some minimal change and get as much as possible from that. So you do something, well, not simple but minimal, and then you get a lot of nice things. So that's the best thing about programming languages. So you need something like core. Like, like Lambda calculus is in the core of any functional programming language. So the best programming language then is just Lambda calculus. You don't need anything else because anything else is just syntactic sugar around it. Okay, so that's one of the possible approaches here. They also think about level of implementation. If something can be done by users, then PL designers don't think about that. Like, for example, in Haskell, for many years, if effects can be implemented on a library level, then there is no use to implement them in the core of a language. It's just meaningless. Why would we do that? Because it's like, let users do that. Or maybe sometimes we can add something into standard library, or maybe we can have some built-in construct, and this is important, adding some keyword, for example. And then if you're adding some keyword to a programming language, then chances are that some developer already use it in their code, and it's just huge pile of problems arise at this very moment. Sometimes some features need runtime support. For example, if we want to implement effects in our language, we need to have some runtime support for that delimited continuation thing. Or if you implement it differently with other styles, there are many possible ways to implement them. Sometimes you need that approach. You need to do something with your runtime, well, if you have runtime in your language. Then they should decide how to expose that feature. Like, it can be just you write that with some keyword or something, or maybe you need to import something. I like this approach from Scala 3, when you import some module, and as a result you get not only some names, but also some algorithms are enabled in order to check your program. That's a very nice idea. Or maybe not very nice, I don't know. I see that some of you might be skeptical here. So you import something, and that enables algorithms in your type checker. Well, it's how they do it sometimes. Or sometimes you write macro call, and that macro generate a lot of code for you, Or if your language doesn't have macros, maybe they have some annotations, like in Java, you're adding annotation, and then just a lot of stuff is generated, and you don't know what's going on out there. You never know. Just a lot of code, like hundreds of lines of code, are generated and compiled. Then, but this is also a possible way. Some folks think about safety. So they want like to control some logic. Sometimes they don't want to do that. It depends. So some of them are also thinking about backward compatibility. So some programming language designers, they know that there are a lot of developers actually writing code in their languages. So they don't want to break anything in their code. So they respect software developers. Sometimes they don't. Well, things happen. Even maybe, so sometimes they are actually thinking about efficiency. And if they do something, they provide you with benchmarks. They say, well, you know, this works too slow. We're not doing that because we don't know how to do that quickly. Sometimes they try different approaches and try to come up with good ideas, how to make it efficient. Sometimes they even think about tooling compatibility. Like they say, oh, well, you know, we have debuggers or profilers, and we need to make sure that they will work after we introduce that change in our runtime system. Sometimes they don't think about that. They just implement everything, and then all of the tools in the ecosystem becomes unusable. Well, that happens as well. So they are concerned with that. And now, like after talking about those criteria, things they are concerned about, we can look at 3 different programming languages, mainly Scala, OCaml, and Haskell, and we can try to compare them a little bit. So maybe they are different somehow in their approaches, how they tackle this problem of introducing effect systems into their languages. So, OCaml. Let's start with OCaml. And yeah, so I am talking about real stuff here. So if we have something in the core of a programming language, that means that it's real. So it's not just research. It's real stuff in industrial programming languages. So in OCaml, they say that their goal was to add native support for asynchronous I/O and lightweight concurrency, so that they want to allow implementing highly scalable concurrent applications. So that was their goal. So in OCaml, they don't think about implementing fancy stuff for functional programmers. No. They want something real. To do that, they introduced recently so-called extensible variant types. It's a type where you can add new constructors at any point in your program. And then with those types, you can do pattern matching, but you are obliged to always provide default case, because it is extensible, and it means that someone else can add something to this type, so you need to think about them. So you have to think about them. And this is one of the ideas behind effects. If you remember that, I told about that in the beginning. So there might be any number of effects. So you have to think that it's possible to have something else. So this was one change. And then another change, they implemented support for delimited continuations at runtime. So it was required to do some things with the call stacks, and OCaml is also like interoperable with the C. So it was important for them to keep stuff for C programs, because sometimes they share the same stack in the memory. And they also thought about debugging stuff. So you implement stack frames. you implement differently, but you still need to make sure that all other tools work here. And they did all that. And with those two things, extensible types, variant types, and this support at runtime, they've added so-called effect module, which is basically it's like maybe 30 or 40 lines of code, so very small, and it's a continuation API. So they in this effect type they give access to the continuation API to those delimited continuations at runtime, and they also allow you to run effectful computations, add effect handlers, and all that stuff. So this is kind of maybe awkward thing because well, continuations are more general, more low-level stuff than effectful programming, but they did it in one single module. They can do it differently because it's experimental. They can change it, so they are allowed to do that. But for now, it's like that. So they said explicitly, we don't need effect safety. So they don't control if there is some effects just going wild and is not handled. They just throw exception and that's it. But the reason behind that was they just don't know how to do that practically good. Because research out there is not ready for that. They don't know how to do that efficient enough with backward compatibility, without bringing a lot of problems to software developers. So they say, well, we'll think about it later, meaning we'll read some more papers in the PL area, and if there is something interesting, then we'll implement it. If not, well, that's fine. We don't need effect safety. So that's OCaml approach. And if you think that I'm making this up, no. You just go yourself and read this paper, retrofitting effect handlers onto OCaml. And the result of that paper was implemented as OCaml. It was called, for many years, it was called multi-core OCaml, and now it's OCaml 5.0. And they actually did that. Full backward compatibility. They prove that this delimited continuation effect stuff doesn't really affect your efficiency of OCaml programs. They did all that, and now OCaml developers can use all this stuff. So that's one approach. Just small example without an attempt to explain everything about effects in OCaml. So this is this model. We are opening it, and they have two kinds of effects, deep and shallow. I'm not going into the difference between them. So this is how they add one new effect, like exchange. This is example from their documentation. They're adding this effect to this extensible variant type, effect.t. And they also, so this is an example of computation. They use this function perform. It comes from effect module. So we have some effect, and we are doing some exchanges there. Another computation, another just doing some effects there. Then I'm skipping like 20 lines of code because they're not relevant. That's effect handler, and I'm not showing it here. And then they can use that effect handler in this code where they run these two computations in concurrent setting. And what's going on actually is that the number from one computation goes to another. So they are exchanging those numbers. So it's basically message passing. And if you look at here, you don't see any message passing here. It's all implemented in those effect handlers. So you write like basically very imperative code here, and then you get concurrency. And it's just 20 lines of code literally here. It's not complicated code. I just don't have enough space in this slide to show it. So that's OCaml. Now, yeah, and the result is like this, because so what they do is 21 goes here, 1 goes here, and then they just get those numbers. Okay, so if you are interested, actually, you can go to the documentation for OCaml, and it's all there. This example. Now, Scala approach. In Scala, well, we don't know what is their main goal. In private communication, I heard this idea that they don't like monadic approaches. They don't like them because they are very type level heavy. It's very difficult for beginners to write monads, to do all that type level stuff. So they want to simplify things in Scala. So, well, maybe that's a motivation. Maybe that's not a motivation. I don't know. Well, I heard that. Then they added one small feature several years ago, which is called contextual functions, and it actually enabled so-called direct style. So you write imperative direct code, but then there is something implicit there, and that implicit adds some more context that can be used by a developer. Another feature, which is relatively new, so-called capturing types, like very new, and it's also experimental right now, adding type safety. And it's actually capability tracking, some special way to track your variables in your code. So they are not adding effects. They are adding low-level features, and it was fun for them to implement those features. But as a result, you get a whole new paradigm of writing code. So that is like an example of what I was talking before. You're doing minimal changes, but then you get a lot of stuff in your programming language, like this whole new shine paradigm of effects systems. They are also going to have some continuation API. It's not there yet, and it depends also on the progress of GVM system, Project Loom, and stuff like that. If you know what I'm talking about, doesn't matter. They have some limited version right now that can be used, where you delimit some part of your program, and then you do something in the middle to implement something like delimited continuation. So this is. Did I skip something? Sorry, I think I skipped one important point. Maybe not. Okay. So this is just an example. I took this example from Noel Welsh. He did his talk an hour ago, and if you didn't look at it, I recommend it highly because, well, it's all recorded. So please look at his talk. He's great at explaining direct style effects, and this is from his blog post. And here what they are doing is just implementing exceptions using effect system. So you have some sort of this part of the code, program phrase, and you can implement that programmatically. You don't need exceptions in the language. You can do that, and you don't have to go over every element. It's like go-to, but in effect systems. So you can do that in Scala now. Now, Haskell approach. I gave up to come up with full features because, well, Haskell is complicated language, dozens of libraries, all that stuff. Very complicated. There are always types there, template Haskell in use, so performance is, well, not very good mostly. That's a small problem, but for Haskell, but still. In some papers, like if you compare sections about performance evaluation for OCaml and performance evaluation for Haskell, it looks very like funny. Like it's just one passage in Haskell paper, we've checked the performance and it's just all right. And then several pages in OCaml paper with just proof that it's all right, with benchmarks and all that stuff. So it's very, very funny to see that difference. there is some progress on implementing continuations into a runtime. We are not there yet. And yeah, that's usual Haskell. They started first, but now they are not there. Maybe in 10 years we'll get back and see. So my conclusion, sorry for taking more time than expected. So you have an idea, you want to bring it into a programming language, and it takes a lot of time. And I admire this idea of adding effects into programming languages because it's fun to watch. So effects are here, and you cannot do anything with that. You will use them. Maybe not now, maybe in a year, in a two, but you will use them in your programming languages, for sure. Is it a good thing? Do we need them? I don't know. We'll see. And this is my conclusion. We don't know what we'll get as a result of this process of introducing effects. Well, let's see, maybe meet later, and that's it. Thank you very much. That's it from me.